Welcome to Math 151. Our lesson today is practice with derivatives. We're going to get some more experience with the power rule and we'll see how that applies in some very special cases. So, reminder of what we went over in the last lesson, that if I have any linear equation, then with slope a and y-intercept b, since the derivative of a constant is 0, and the derivative of something times x is just that something. So the derivative is just the slope, and that makes perfect sense because that's what the derivative tells us, is the slope of the tangent line. Well, every line on this between 2 points on a linear equation has slope a, so the derivative is a. And we prove this using the limit definition. The derivative of x to the nth power is n times x to the n minus 1. That is, I bring down the exponent, and then x has an exponent reduced by 1. And because a derivative is a limit, if I make a linear combination of functions, constant r times g of x plus the constant s times h of x, then I can do two things. The derivative of the sum is the sum of the derivatives, because the limit of the sum is the sum of the limits, and I can pull constants out of derivatives. So f prime would be r times g prime plus s times h prime. And we use that to show that we can extend the power rule to the derivative of a polynomial. Let's look at some examples. So f of x is 8x cubed plus 2x squared minus 5x plus 7. The derivative, using the rules we had above, the derivative of the sum is the sum of the derivatives. So I can take the derivative of 8x cubed and then add the derivative of 2x squared and then add the derivative of negative 5x and add the derivative of 7. So the derivative of 8x cubed, I can bring the constant out. It's 8 times the derivative of x cubed. The derivative of x cubed is 3x squared by the power rule. And then I add the derivative of 2x squared. Well, that's 2 times the derivative of x squared. The derivative of negative 5x is negative 5, and the derivative of 7 is 0. I guess we can put that in for emphasis. The derivative of a constant is 0. So 3 8s are 24. 2 times 2 is 4. So the derivative of the original function is 24x squared plus 4x minus 5. Another example of using the power rule: if f of x is x to the 25th plus x to the 13th, then the derivative is 25x to the 24th plus 13x to the 12th. Notice how I brought down the exponent in both cases and reduced the exponent by 1. The derivative of the function f of x equals pi is 0. Why? Because pi is a constant. Pi is about 3.14159. It doesn't change, so its rate of change is 0. So that's true for any constant. And the power rule that says that if f of x is x to the n, f prime of x is n times x to the n minus 1, it works even if n is a negative integer or a fraction. Remember, for example, that x to the minus n really means 1 over x to the n. A negative exponent signifies division. Why is that so? Well, consider x to the n times x to the minus n. Remember the rule for exponents: when I multiply, I add exponents. So this means x to the n minus n, or x to the 0. And anything raised to the 0 power is 1, as long as x isn't 0. So what have I shown? X to the n times x to the negative n gives me 1, so they must be inverses, reciprocals of each other. So x to the minus n must be 1 over x to the n. So here are some examples of using the power rule for negative exponents and rational or fractional exponents. If f of x is x to the minus 4, the derivative, f prime of x, is negative 4 times x, notice, to the minus 5. Because if I subtract 1 from negative 4, I don't get negative 3. If I subtract 1, I get negative 5. If if the function is x to the minus 7, then its derivative is minus 7x to the negative 8. Subtracting 1 from negative 7 gives me negative 8. And if f of x is x to the 5/3, then f prime of x is 5/3 x to the 2/3. Why? If I subtract 1 from 5/3, that's the same as subtracting 3/3. I'm left with 2/3. So that's the derivative in the exponent case. But fractional exponents have a special meaning. So remember that if f of x is the square root of x, I can also signify that by x to the 1/2. Why? Well, what would x to the 1/2 squared be? Squaring means multiply the element by itself. So this is x to the 1/2 times x to the 1/2. But by this power rule we just talked about, multiplying means adding exponents. This is x to the 1/2 plus 1/2. But that's just x to the 1, which is x. So what happened? The thing I squared gave me x, so that thing must be the square root of x. So x to the 1/2 is the square root of x. So now we can use the power rule on roots. If f of x is the square root of x, that's the same as saying f of x is x to the 1/2. So the derivative is 1/2 x to the minus 1/2. Why? Because if I subtract 1 from a half, I get negative 1/2. But again, using the fact that negative exponents mean division, this is 1/2 of 1 over x to the 1/2. But x to the 1/2 is the square root of x. So the derivative of the square root of x is 1 over 2 the square root of x, just by using the power rule. In a similar way, if f of x is the cube root of x, that's the same as x to the 1/3 power, because x to the 1/3 times x to the 1/3 times x to the 1/3 is x to the 1, or x. So this x to the 1/3 represents the cube root of x. So the derivative then would be 1/3 x to the minus 2/3, because if I subtract 1 from 1/3, I get negative 2/3. And again, the negative exponent signifies it should be division, so it's actually 1 over 3 times x to the 2/3. But what is x to the 2/3? Well, the 2 means square, but divide by 3, this is like x to the 1/2 to the 1/3 power. So that's the cube root of x squared. Again, the meaning of fractional exponents. So the derivative of the cube root of x is 1 over 3 times the cube root of x squared. Some applications. So the curve below is described by y equals the square root of x for x greater than 0, because negative values don't produce a real number when I take the square root. We want to determine the equation of the tangent line to the curve at x equals 4. So there's the x value here. We want it at that point. If you think you can do this, you can pause the video here, and then we'll go over the steps. If you want to see the steps, just continue the video. So here we continue. How do we do this? Well, with several steps. First thing we want to do is determine the y value that goes with x equals 4. That's easy. Just plug 4 into the function. The function is y equals the square root of x, so the y value associated with x equals 4 is the square root of 4, or 2. So the point 4, 2 is on the curve, and that matches the graph. Here's 4, and that point is about y equals 2. The next thing is we use the derivative. We want to determine the derivative y prime, or dy dx. Well, y is the square root of x. That's the same as x to the 1/2. So the derivative is 1/2 x to the minus 1/2, or 1 over 2 times the square root of x, as we showed before. But now we have the derivative, we can use it to determine the slope of the tangent line. We simply plug 4, the x value, into the derivative. So my m, my slope of my tangent line, is y prime, the derivative evaluated at my x of 4. Well, that's 1 over 2 times the square root of 4. The square root of 4 is, of course, 2. That's 1 over 2 times 2, or 1/4. So the slope of my tangent line is 1/4. And finally, I determine the y-intercept using a point. Remember, b is a y value minus m times the x value that goes with that y value. We have a point on the curve with x equals 4 and y equals 2. So there's y minus m minus 1/4 x. And of course, 1/4 times 4 is 1. That's 2 minus 1, and that's 1. So my y-intercept is 1. So now we have a slope, a quarter, and an intercept, 1. We can build the tangent line. It has equation y equals 1/4 x plus 1. And if we plot that line and the point at 4, 2, we can see it indeed looks like a tangent line. And you can do this on your calculator by plotting both the curve y equals the square root of x and the curve y equals 1/4 x plus 1. You should get a similar result on your graphing calculator. Okay, now it's your turn to do some work. So given g of x is 3x to the 5th minus 5x cubed plus 4x, determine g prime using the power rule and the other rules. If h of t is t to the 2/3 plus t to the minus 3, determine h prime of t. And determine the equation of the tangent line to the curve y equals 5x to the 1/3, or 5 times the cube root of x, at x equals 27. And remember, 3 cubed is 27, so the cube root of 27 is 3. So please pause the video here, work those exercises, and then we'll review the solutions together. Okay, hopefully that went well. Hopefully you were able to solve these exercises. Let's review the solutions. In the first case, it's very easy to apply the power rule and the other rules that help us take the derivative of a polynomial. For g of x, the derivative is 3 times the derivative of x to the 5th. That's 3 times 5x to the 4th, minus 5 times the derivative of x cubed, which is 3x squared. And then the derivative of 4x is 4. So the answer is 3 times 5 is 15. 15x to the 4th minus 15x squared plus 4. In the next exercise, h of t, the derivative is 2/3 t to the minus 1/3 minus 3 times t to the minus 4. Again, using the power rule, in this case for fractional and negative exponents. The last one, we have a lot of work to do to build the tangent line. We need a y value associated with x equals 27. Well, that's 5 times the cube root of 27, which is 3. So 5 times 3 is 15. So the y value associated with x equals 27 is 15. And so that's a point on the curve. Then we compute the derivative using the power rule. The derivative is 5 times the derivative of x to the 1/3, or 5 times 1/3 x to the minus 2/3. That's the same as 5/3 times 1 over x to the 2/3. To find the slope, I apply the derivative. The slope is y prime evaluated at 27. So it's 5/3 times 1 over 27 to the 2/3 power. Well, I can do this in steps. I can take the cube root first, giving me 3, and then square it, giving me 9. So this is 5/3 times 1/9, or 5 over 27. Finally, the intercept is y minus mx. So I take my y value of 15 minus the slope, 5/27, times my x value of 27. That's actually 15 minus 5, or 10. So the tangent line has equation y equals mx plus b, 5/27x plus 10. And here's a picture of the curve, the cube root of x, along with my point of tangency at 27, 15, and my tangent line with slope 5/27 and y-intercept of 10. Okay, so that's our lesson for today. For homework, please study section 2.2 in our textbook up to theorem 2.5 and example 7. Those are found, at least in my version of the book, on theorem 2.5 and example 7, page 94. And then work the following exercises from section 2.2. Number 2, number 3, number 4, number 5, number 8, and number 10. We'll review those at the beginning of class and work several more exercises from this section on Wednesday. That ends our lesson for today.